Hey guys, welcome to Mathletics. In today's video, I will demonstrate how we can use differential equations to express the population trends of two species which are competing for the same food. This is basically a modeling situation for using differential equations. So suppose we have a resource, or you can say food, and we have a population X and a population Y, and they're both trying to feed off this resource. So how will these populations change with time? We assume the population of each species is governed by the logistic growth equation to which we will add a factor. So a logistic growth equation for x would be dx dt x times epsilon 1 minus sigma 1 x, where this is the growth rate of x and this is x decreasing food by eating it. Same for y. dy over dt is equal to y times epsilon 2 minus sigma 2y. Again, this is the growth rate and this is just y decreasing the food, because of which its growth decreases. Now this is if x and y were in separate arenas. Basically, they had separate resources or separate food. But if they are together in the same place, they will eat each other's food too. So we have to add another factor, which we say alpha 1 times y and alpha 2 times x. These alphas are what we call degree of influence. So if we add these equations to our above equations, they become x times epsilon 1 minus sigma 1x minus alpha 1y, and dy over dt is equal to y times epsilon 1 minus sigma 2y minus alpha 2x. These both, they decrease the growth rates because the other eats their food. So whatever the growth rate of x was before, now it's slower because y, being in the same place as x, is also eating x's food. Now this whole system is nonlinear. So we are going to try to estimate a linear system whose trajectories or behaviors are easy to describe. Suppose we have a nonlinear system and that x 0 is a critical point of the system. Recall that a critical point means that the derivative at zeros are zeros. So if this column vector here, G, is small enough near 0, then we can say that x prime is equal to ax is close plus g, excuse me, is close enough to this, and this is almost linear. Now, take a general system for our population problem. We're going back to our population problem, which was x prime is equal to f of x and y. I'm just describing this whole thing as a function of x and y. And we'll let y prime is equal to be g of x and y. And let xo and yo be a critical point. Remember, these two are describing the behaviors of two competing species. This system is almost linear in the neighborhood of this critical point. Using Taylor expansions about this critical point, we can form a linear approximation using the first 3 terms of the series. What I mean is we can write x prime as f at xo plus f of x times x minus xo plus f of y minus yo. Same for y prime. Okay, so if we can write this in matrix notation, if you don't know again what happened here and here, this is just a linear approximation of a function of both of these functions, and we are getting this approximation from the first 3 terms of the Taylor expansion of each of these functions. So again, writing these in matrix notation, we will get x prime, y prime is equal to f of xo and yo, g of xo, yo, plus f of x, xo, yo, g of x of the same thing, xo, yo, f of y, and g of y times x minus xo, y minus yo. Now this thing is what we call a Jacobian matrix. You might recall this from Calc 3. Now if we want to write this simpler, we can write y prime, x prime, y prime is equal to f of x of xo, yo, g of xo, yo, plus the Jacobian matrix at xo, yo times x minus xo, y minus yo. Now at critical point, x, o, y, o, f and g are equal to 0. Remember that they equal the derivatives of x and y. So at a critical point, the derivatives are 0. So at x, o, y, o, f and g are equal to 0. And because of linearity, we say that x minus xo is just x, and y minus yo is just y. This is a bit of an approximation. So now using these facts, let's rewrite this thing. Then we would write this as x prime y prime is equal to jxo yo x y. Or this is the same as x prime is equal to j x. Now let's see how we can use this information to describe the behavior of trajectories of two populations. With an example, let's say we have dx over dt is equal to x, 1 minus x minus y, dy over dt as y, 1.5 minus y minus x. And now we want to describe the behavior of these two populations. First order of business is to find the critical points. This is because we are assuming linearity around them. Critical points mean that these are equal to 0. Now you can see that 0, 0 is a critical point because x equals 0 from here and y equals 0 from here. Now if we solve 1 minus x minus y times x is equal to 0 and 1.5 minus y minus x times y is equal to 0, if we do this together, you'll find the other two critical points. What I'm going to do is I'm going to let y be 0, then we get x as 1. And then I'm going to let x be 0, then I get y as 1.5. Now these actually check out. You can check these by plugging them in into these three coordinates, you can say, or x and y's, and they will check out to come out as 0. So we have our three critical points, which are these. Next, what we're going to do is we are going to write our Jacobian. We said our Jacobian, it was fx, fy, g of x, and g of y. So this is also our f and also our g. Remember, x, y, and x prime is what we defined as f and g. So taking the partial derivatives, we have f of x is equal to 1 minus 2x minus y, f of y as minus x, g of x as minus y, and g of y as 1.5 minus 2y minus x. Now as x prime is equal to j times x, we are basically back to a system of linear equations. Remember, we were doing till now something like this. This is the same thing, basically the same form. And we can solve this now using eigenvalues and eigenvectors like we have been doing until now. And we have to do this for each of our critical points. So our first critical point, 0, 0. Our Jacobian for the first point, we will get the Jacobian for the first point of all of our points by plugging in the x and y's into all of these. So plugging in 0 for f of x, 0, 0, I will get 1. For f of y, I will get 0. For g of x, I will get 0. And for g of y, I will get 1.5. Now we can solve for the eigenvalues using our characteristic equation. In this example right now, this is a, so we get lambda squared minus 2.5 lambda plus 1.5 is equal to 0. Solve this out and you will get lambda is equal to 3 over 2 and 1. Now these both are real and positive, so they show an unstable nodal source. If you are uncertain of what different kinds of eigenvalues represent on a graph and about their stability, I'm going to show it at the end of this video, so do watch it till the end and you can take a screenshot or write down all of those phase portraits for different types of eigenvalues and their stabilities. So for our second critical point, we have 0 and 1.5. So our Jacobian, again, I'm going to plug in 0 and 1.5 into each of these as part of my Jacobian. And then I will get negative 0.5, 0, negative 1.5, negative 1.5. Again, using the characteristic equation, it becomes lambda squared plus 2 lambda plus 0.75 is equal to 0. Solving this gives me minus half and minus 3 over 2. Now both of these are real and they're both negative. So this represents an asymptotically stable nodal sink. And for the last time, for my third critical point, which is 1, 0, I have 1, negative 1, 0, 0.5. So I think this is negative 1. Once again, I got these values by plugging in 1 and 0 over here for my Jacobian. So the characteristic equation, now I'm going to assume that this is A. This gives me lambda squared plus 0.5 lambda minus 0.5 is equal to 0. Solving this gives me half and negative 1. These are both real with one positive and one negative, which means that this represents a an unstable saddle point. You have the eigenvalues. You can very well go ahead and solve for eigenvectors for all of these. But for the purpose of just describing the behavior, we don't need that. We only need this information and our critical points. So now to plot all of this, we have x here and y here. Now what we're going to do is plot our critical points. So we had a 0, 0. We have a 0, 1.5. And we have a 1, 0. Okay, so our 0, 0 is an unstable nodal source, which means it's got stuff coming out of it. For now, let's put it like this. Our 1, 0, we said, is an unstable saddle point. So which means if it's got stuff coming in from here, it's got stuff coming in from here, and stuff going out from this side. We said our 0, 1.5 was a real asymptotically stable nodal sink, which means it's got stuff coming in. Even close to it, we've got stuff coming in. Now we just gotta close all of these trajectories and kind of connect them. So you can see that we've got stuff going in right here, and we have stuff coming out of here. So you can just connect this to here. We've got something going all over here, but our trajectory shows that things from here follow this path. So we're just gonna let them all go over there. And this place right here shows that trajectories move something like this, to the right and up, to the right and up. You can add more paths, but you kind of get a hang of it. So the whole point of plotting these critical points and seeing what the trajectories around them are doing, we're just trying to see what the whole plot is going to look like. So we're just plotting what's near the critical points and then just connecting the trajectories. So I hope this kind of explained the whole concept of competing species to you guys. And if you have any questions, put it in the comments. I'll try my best to answer. And as I said, I have put in all the phase portraits and stabilities at the end. So here they are. There are quite a bit of them, so I'm going to just pause for some time for each of them, and you can, I don't know, maybe take a screenshot or keep them or put them down on paper. Thank you guys for watching the video, and I'll see you guys very, very soon.